Swayam Prabha. Digital India. Educated India.
Suppose, say, look at this vector x minus y. Okay. We want to see that will this be an eigenvector for some eigenvalue. Right. So, if suppose I look at the matrix, say 0 b, b transpose 0 with x and minus y. So, what would be this? So, we get minus by and b transpose x, and we already know that by from the previous representation, by is nothing but lambda x, right, and b transpose x is lambda y. So, putting it back here, you get this is minus lambda x. So, this would be minus lambda x and this is lambda y. So, pulling minus lambda out, you get x minus y. So, starting from b into a vector, b, I mean the adjacency matrix into a vector, we have arrived at minus lambda into the same vector, right. So, we can see that minus lambda is going to be an eigenvalue with the corresponding eigenvector being x minus y. Okay. So, therefore, we can conclude that if lambda is an eigenvalue, and this is going to happen for how many ever times this lambda repeats, right. If eigenvalue, if lambda is an eigenvalue of multiplicity k, then minus lambda is an eigenvalue of we are talking about eigenvalue of A with multiplicity k. So, this is another beautiful thing that you can see. If you have a bipartite graph, your eigenvalues occurs in pairs, lambda, minus lambda and so on. Of course, rank is not 2, so it could whenever it occurs in pairs. So, I will give an exercise for you people, like try to find the spectrum of cycle graph Cn or path graph Pn. So, take this as an exercise, you can solve it later. So, next what we want to talk about is, we will try to finally characterize more about these bipartite graphs, but before we do that, we want to give a representation of determinants in terms of elementary subgraphs. Okay. So, what are elementary subgraphs? So, given a graph G, I say H is a subgraph of G and H is elementary if every component of H is either a cycle or an edge. So, every component of the subgraph is either an edge or it can have, I mean we permit only cycles. Okay. Do not ask me, a cycle also has edges, we mean components are just singleton edges, like you just have an edge on two vertices. Okay. So, no other components are permitted here. Okay. So, any subgraph, if it is of elementary subgraph, then we want to represent it this way. Say for example, let us revert back to our K4 minus E. So, if suppose I want to look at a subgraph on the vertices say 1, 2, 4. So, my V is say 1, 2, 4. What could be my edge set? As an elementary subgraph. Can I have an elementary subgraph on this? Okay, say suppose I take another one. V3. So, the edge set could be just the pair 1, 3, right. So, this is an elementary subgraph, but here if you see 1, 2, 4, we cannot have an elementary subgraph because 1, 2, 4 they form either a path P3 or we cannot split them into two edges because we are talking about subgraph induced, right. So, in that case I mean not induced, we are talking about subgraphs. So, we cannot have 1 and 2 components, like I cannot write it as 1, 2 in one component and 1, 4 as second component, that is not possible. So, this with this vertex set I cannot have an elementary subgraph. Okay. But whereas for the other one we can have. So, there is also another what do we say, next level for this, we call an elementary subgraph to be spanning if every vertex is there in my subgraph. Okay, every vertex is included, or vertex set of H is equal to vertex set of G. In that case, then we call it as spanning subgraph. So, how many elementary spanning subgraphs are possible here? So, since we said spanning, all the vertices are going to be there, right. So, I will just give the edge set. My edge set 1 could be like, say, the pair 1 2 as an edge, and the second component could be 3 4, because 1 2 is gone. So, 3 4 is the only left out possibility, right. So, this is one possible spanning elementary subgraph. So, when I write 1 2, I mean the edge 1 2, this is one component, 3 4 is another component, right. Similarly, if we look at another subgraph, so we can have 1 4 and 2 3, right, and there is another subgraph possible. What is that? 1 2 3 4, the whole all cycle, right. Yeah. So, I can just write it as, I will write it as a cycle itself, 1 2 3 4. So, there are 3 possible elementary spanning subgraphs for this given graph. Okay. So, why are we doing this? We will go into the representation. So, in an elementary subgraph representation, we will now start counting the number of cycles that the subgraph has, that is the number of components which are cycles and number of components which are edges. Okay. Say suppose I give the notation, say C of G for number of components of H, sorry I am talking about H. So, C of H to be number of components of H which are cycles, and similarly we can have a representation for say C1 of H, which is going to be number of components of H which are edges. So, with this representation we will now go into another way of writing the determinants. Okay. We know, we have seen at least 2 different formulas now, right, for determinants. So, one was using the principal minus, the usual standard one, how we write minus 1 to the power of I plus j into determinant of aij, leaving I and jth row, ith row and jth column, we write it that way, right, using the principal minus, right, sorry, using the minus. Now, there is also another way to write. So, given a matrix A, in fact, we are talking about a graph. So, an adjacency matrix, say of order n by n, right. So, determinant of this matrix that we are talking about, A minus lambda I, or determinant of A, what we are talking about is summation over minus 1 to the power of n minus this number of G is only coming to me. Okay, C1H, the number of edges as components in H, and minus number of cycles as components in H, okay, into 2 to the power of C of H. Okay, that is number of cycles that is possible. Okay. So, where H is nothing but a spanning elementary subgraph of G. Summation is taken over all possible spanning elementary subgraphs. So, how do we arrive at this formula? So, let us go back to our original representation using permutations, right. So, there we had our determinant was nothing but sigma minus 1, sorry, we had sign of a permutation, say pi into A1 pi 1, A2 pi 2 and so on, An pi n, right. This is what we had before, and where pi is nothing but taken over all permutations on n vertices on the n element set, right. So, now if you look at this in our setting, in our adjacency matrix setting, look at any non-zero term in the summation. What does that mean? Any non-zero term in the summation. So, let me pick out one non-zero term, say for a1 pi 1, a2 pi 2 and so on, an pi n. Say if I claim that this is a non-zero term, if determinant is non-zero, that if there is a, I mean if my matrix has determinant non-zero, that means there is at least one term which should give that non-zero value, right. Not all terms could become 0 simultaneously. So, what does this mean? When we talk about this representation, it is nothing but product of n elements of the matrix, right. And this is non-zero means what? In adjacency matrix, we are talking about everything is 0 or 1, right. So, we have a1 pi 1 should be 1, right. All these terms should be just 1, only then you will get a non-zero term. That means what? This permutation gives me that it takes me into account all the edges that are possible, right. a1 pi 1, a2 pi 2 and so on. This takes into account all the edges that are possible here, right, for this one particular term, right. So, if I just pull out these kind of terms outside of this sum, we are like looking at the possibility of this being in this permutation. I may also have, and cycle is also possible, right. So, we can see that only cycles and edges are being counted in these terms. Each of these non-zero terms gives me cycles and edges that are present here, right, because this permutation could have a cycle in itself. So, that means what? My pi will, if it has a cycle, then I am talking about elementary cycle existing in my subgraph. Right. So, that is how we pull out this idea of elementary subgraph, and where this minus 1 to the power of n, that term corresponds to this sign of the permutation. Okay. So, sign of this permutation, what we are talking about is going to be nothing but minus 1 to the power of n minus C1 of g minus C of g. Number of cycles out of my permutation, I am just going to look at all cycles, how many ever cycles, because we have to count ultimately even or odd, right, every permutation whether it is even or odd. So, in that case you just remove all those edges, because every edge is going to account for a transposition, right. In my permutation, if I have a permutation 1, 2, 3, 4 up to 4, say I just have, if suppose I have this permutation corresponds to an edge, right, 1, 2, this is actually 1, 2, right, a transposition 1, 2, this corresponds to an edge, there is an edge between this where 3 and 4 are fixed, right. So, in this sense we can easily see that the translation goes into edges, and if we have a cyclic permutation inside this, that also will account for the number of even or odd permutations. So, we are just removing that from our n, okay, to give us the positive or negative sign. So, this accounts for the sign of the permutation here. Okay. And what about this 2 power ch? Why do we need this term? So, I have justified you for why such a term is going to exist. First of all, 2 power ch, if you see any cycle, c is nothing but the number of cycles, right, in my component. So, any cycle I can account it in 2 directions, right. In my permutations I may have a cycle 1, 2, 3, 4 or 1, 4, 3, 2, right, both represent the same cycle, right. A permutation, in my permutation I have 2 ways of counting the same cycle, right. So, therefore, we will have this 2 power ch. Suppose I have in my elementary subgraph a cycle, I can either count it as a permutation, the cyclic permutation in one direction or going in the other direction, because we are anyway having undirected graph. If it is directed, then the scenario will change, but for undirected graphs we have this. So, we have to take into account that also. There are 2 possibilities for counting the cycles. So, this is another representation which is quite easy to see and quite easy to compute also. You just need to look at the all possible elementary subgraphs coming from the graph and then just represent it, right. So, now going back to this example, what will be the value for each of this h1? So, if I want to take the sum for this, and there are, we have seen for this example there are only 3 elementary subgraphs H1, H2, H3, right. So, what will be the determinant for this? Without computing determinant we can do it through this formula. Say for H1, what do I have? Minus 1 to the power of n minus, so I have only exactly 2 what do we call, 2 edges are there, right. So, it is going to be, so first of all my n is 4, so 4 minus 2 and there are no cycles, so 0 into 2 power 0, right. So, this is going to account for 1, right. Similarly, if I look at H2, what about H2? I will have same value because they also have 2 edges. So, H1 also has the same value here, it will also be the same thing, right. What about H3? Minus 1 to the power of 4 minus 0, there is only one cycle, right. So, 4 minus 1 into 2 power 1. So, which is going to be equal to minus 2. So, if you look at the determinant, my determinant is going to be nothing but 1 plus 1 minus 2 here, right, because we have 2 times. So, I will just go to the next page, so it would be clear. So, determinant would be nothing but 1 plus 1 for H1. So, this is for H1, this would be for H2 and minus 2 for H3. So, we can see that the determinant of this graph is, this adjacency matrix is 0, right. That you could have also seen from the expression also there, right. Okay. So, why did we do this? To further explore about our characteristic polynomials, okay. So, now from this representation, what can we say about the coefficients in my representation? If I mean, we have already given 2 ways of writing the determinants here, right. One is using this minus 1 to the power of, the formula is there, and the other one is also permutation, using the permutation we have this formula, right. What about my other polynomial representation? Suppose already we have seen this, right, my determinant of a minus lambda I is, if suppose I look at it in this fashion, I will just rewrite this formula, say lambda power n plus say b1 lambda power n minus 1 plus b2 lambda power n minus 2 and so on, you have bn. I have now, you just see here the characteristic polynomial, I have rewritten it. In the previous place I was writing it as in the reverse order, now I am just writing it so it is easy to represent. So, if you look at these coefficients bk, we know each of this bk is nothing but sum of all principal minors, right. So, how can I connect this with the formula over here? Okay, I will give you the this one. Then bk is nothing but minus 1 to the power of c of h, c1 of h plus c of h into 2 power c of h, where my h is nothing but all elementary subgraphs of order k, right. So far in the main formula, what did we do? We took spanning subgraphs, but now since we are going to look at every coefficient, how does the coefficient get connected to this formula? It is nothing but h is elementary subgraph of G of order k, and you do this over all possible order k subgraphs. Okay, think of this. If I look at the principal minus, okay, in this of order k, right, if we try to prove this, you look at the principal minus, how will we write the representation for any bk term? How do we write it? The bk term was nothing but minus 1 to the power of k into sum of all principal minors, right, principal minors of order k, right. This is what we are looking at, but what is this principal minors here? The principal minors, you take k vertices at a time, right, that is what your submatrix is giving you, k rows and k columns, identical rows and columns we are taking, right. So, that gives you nothing but the k subgraph, right, the order k subgraph of the given graph, right. So from there we can easily see that this would be nothing but, if I think of that subgraph as my whole graph, then what will the summation be for Bk? It would be just nothing but sigma minus 1 to the power of k minus C1h minus C of h into 2 power C of h, and summation over all such order k subgraphs. Okay. So this is where we can connect the principal minus with the subgraphs and this elementary subgraphs of order k here. So here what can we say about the B1? What will be B1? B1 means what? Elementary subgraphs of order 1, right? We are trying to look at all possible elementary subgraphs of order 1. Do we have an elementary subgraph with one vertex? No, we need at least 2, because we need an edge, right? At least an edge should be present there, right? So we can immediately see that your B1 is going to be equal to 0. So suppose, if I extend this argument, suppose my B3, see B1 because one single vertex I can get rid of. What about B3? Only triangles is possible, right? I cannot have an edge, path, nothing else, right? So when will B3 vanish? When there is no triangles, right? So extending this, I can see that the B3 vanishes when there is no triangle, right? In my graph, we are talking about in our graph, because we are looking at all possible 3 vertex subgraphs, right? So in that there is no triangle. Similarly, if we think about B5, because even vertices there could be edges possible and cycles are also possible, but for odd vertices the only possibility is we can count this entity here only with cycles, right, with odd number of vertices, because we cannot have like 2 edges and a singleton vertex standing there, right, hanging over. So the only possibility for the contributors for these coefficients B3, B5 are cycles in case of odd numbers, right, B3, B5, B7 the coefficients are accounted only using the odd cycles that are present in the graph, right. So we can see that B5 will be 0 when there is no C5, right, when there is no 5 cycle, I could say, and so on. We can just extend this argument for any number of k, right. So this is where we want to touch upon bipartite graph. So suppose all these coefficients B3, B5, B7 and so on until say B2 k plus 1, where this is going to be the largest possible cycle or entity here, right. Suppose all these are 0, then what can I say? Say 2k plus 1 is less than or equal to n. Just keep. Yeah, so this means what? If suppose all these are 0, that means we have no 3 cycle, 5 cycle, 7 cycle, so no odd cycles are present. So therefore my G is bipartite, right. So now we will go into our characterization. Now we will combine all these results what we have seen connecting to the bipartite graph. So we have an equivalent theorem which says that the following statements are all equivalent about a bipartite graph. So one is G is bipartite, 2, if we look at the characteristic polynomial, what we have recently seen, the characteristic polynomial phi g of lambda written in this fashion. So lambda power n plus say b1 lambda power n minus 1 plus b2 lambda power n minus 2 and so on plus bn. In this characteristic polynomial, if phi is this, then all b to k plus 1 is 0, where k runs between 1 and I can say n or n by 2, whatever, you can just understand this fact, right. and the third one is the eigenvalues of A are symmetric with respect to origin. By origin I mean the 0 vector, the 0 value, I am sorry. Okay. So, by symmetric what we mean, if lambda is an eigenvalue, then minus lambda is going to be an eigenvalue, right. So, that is if lambda is an eigenvalue with multiplicity k, then minus lambda is an eigenvalue with multiplicity k. Bipartite. This is for bipartite. Maybe for other graphs may also satisfy this, which are not bipartite, but they may be very special cases. Oh wait, no, it's an equivalent statement I am talking about, I am sorry. If G is bipartite, then the statement is true. If the statement is true, then G has to be bipartite. It is equivalent, 1 implies 2, 2 implies 3, 3, I mean 1 is equivalent to 2, 2 is equivalent to 3 and 3 is equivalent to 1. Thanks. Any bipartite graph, and if it happens then my graph has to be bipartite. This is how we characterize from the eigenvalues. Given a spectrum, the next problem what we will see is, without looking at what kind of graph we are having, can I just tell by looking at the eigenvalues, this is the class of graph. Say suppose I give you an eigenvalue, a spectrum, say possibly say like this, I have a spectrum like this. Can you tell me for which graph this spectrum is going to hold true? We have seen this somewhere, recently we have just seen it. Yes? Bipartite. Bipartite graphs will have, just now we said, right, it should have paired eigenvalues. If 3 is there, then I should have a minus 3. See here, by this notation what we mean, I have a minus 1 eigenvalue which repeats 3 times, and 3 is an eigenvalue which repeats or occurs once, right. This is also another alternating representation for what do we call the spectrum. In some books they follow this as a notation where they write the eigenvalue as a power will be the multiplicity, but it is not power, but we just write the multiplicity there. For which graph is it? K4, right? K4 has n minus 1 as one eigenvalue and minus 1 n minus 1 times. So, these classes of graphs are completely characterized, have been characterized. If I give you an eigenvalue, I can immediately say what kind of graph it is. Okay. So, one way of the study of spectral graph theory is to characterize graphs through the spectral properties. So, for example, bipartite graphs are completely solved, complete graphs are solved. Similarly, cycles, Cn, if you go, Cn also has a very special formula for your spectral, I mean eigenvalues and the corresponding eigenvectors. Similarly, path graph, and there is also another nice property for hypercube. So, I will give this as an exercise. Find the spectrum of hypercube. You guys know hypercube, right? Okay, then I will not give that exercise, but we will give you the definition and then give you the exercise. I have couple of minutes, I can just take to give the exercise. Yeah. Okay. So, the first problem sheet for you, I did not prepare the problem sheet, so I am giving you here. So, find the spectrum of Cn. So, one thing is, do not look into any internet, these are all available because these are well studied classes, solve it yourself. Okay. So, spectrum of path graph, a path on n vertices. And for those who know, you can think about spectrum of Peterson graphs and hypercube graphs. Okay. So, when we come back, we will continue with regular graphs, which we have not seen. So, next we will see whether is there any characterization for regular graphs, that is graph with degree, all degrees having same, all vertices having same degree, right. And we will also digress into other classes of matrices. More than adjacency matrix, there is another class of matrix which plays a very important role in the spectral theory, which is also used for lots of graph drawing and representations. So, that we will see in the forthcoming classes.